Happy to get us started. All right, guys. We will go ahead and get started. Thank you so much for coming. I'm not sure if you saw Julia's email, but we're just going to be going over the questions that touch on Unit 3. We do recommend that you go and review the feedback on midterm 1 and midterm 2 that we gave you. Lots of the questions will be overlapping or may even be the same. If you have questions on the midterm 1 and midterm 2 material, or like units 1 and 2 material at the end of going over unit 3, then we will stay a little bit after if needed. We'll try to leave time for questions even during this hour, but yeah, do you have anything to add, Julia?
I think so.
Yeah, it's the same format as the other exams, and you can turn in whatever you'd like in terms of whether your answers are written or typed. So
I guess the final is a little bit longer than the midterm.
that is true.
So expect for it to take a good amount of time. And it's cumulative, so it will be a longer exam. It should be pretty similar to the length of this one. This was ours from last year. So
I think I think there are around 14 short answer questions, and then I think 3 long answer portions.
maybe 4.
Or 4 long answer portions.
Probably almost double.
Almost twice as long as the midterms. So I would make sure to set aside time.
It's a hefty one. But we believe in you guys, and I hope you find that with a lot of the questions from the first half of class, like it should be a lot of stuff you've seen before. And we're gonna go over the stuff you haven't seen before. So
and I really do feel like you're well prepared. I was so blown away with how well everybody did on midterm 1 and midterm 2. And so really just be confident going into this.
Yeah, you guys are doing great. So we have not seen the exam. It doesn't exist yet. So we can't we can't guarantee we don't have solid answers for some of your potential questions. So one thing I would suggest is just pay attention to the wording on the test. Sometimes what happens is we might have questions that are very similar to the review that we give you. We saw that happen a little bit with midterm 2. There were a couple questions that got most of you, and we weren't doing that on purpose because we didn't know that was some of those questions would be different on the final. And so just pay attention to that, because we can help you with these practice exams, but it's pretty common that Jocelyn might take a question and slightly change it so that you're doing one step a little bit different. So just be careful to read the questions very carefully. But yeah. Okay, any general questions about the exam before we get into these? Okay, so I think you're first, Anna.
Awesome. Yes. And I won't be writing anything down.
I'll just
for
write it
these
for you
ones,
then.
But
I'll write it.
okay, so if you are looking at the practice exam, the first one that I'm going to go over is number 4, which asks, what are the 4 causes of endogeneity discussed in class? Is there anyone who can tell me what endogeneity is? Kyra, or sorry, Chris, either of you.
I was just gonna say outside variables that are influencing your results that you are not.
Yeah.
Your models.
Yeah, so endogeneity is when there's a correlation between what's in the error term and your X variables or your independent variables. And this is a problem because, of course, we're trying to isolate the relationship between X and Y. And if there are variables contained in the error term that aren't accounted for in the model, then if X is correlated with those variables, then we might see a relationship between X and Y that we think is real, but it's really not, because we're actually picking up on something that's contained in the error term. So I'll just very briefly go over what those 4 causes of endogeneity are. So the first is when you accidentally use a linear model and you should be using something else like that S curve. Maybe you would want to estimate like a logit or probit, or maybe, or I guess not. Just scratch what I just said, because that would be contingent on you having a binary dependent variable. But maybe you need to transform the data with like a squared term or a log or something like that. So the first cause of endogeneity is using a linear model when the data is not in fact linear. The second is measurement error, which is when the actual reports of X are wrong. And if you think about it, it makes sense that if X was wrong, or like if you had false reports on X, then maybe it's correlated with the error term in unique ways. And so you're really not isolating that relationship between X and Y like you want to. I think that the examples that Jocelyn gave in class for measurement error, like of course, there is measurement error that just happens by nature of the fact that we're human, and maybe people, I don't know, maybe they misunderstand the question. And so that would be measurement error. But maybe they also don't want to report their actual height or weight for some reason, or how often they have sex, that kind of a thing. So that's an example of measurement error. Number 3 is simultaneity. And this is where there are two variables that are mutually influencing the other in like a cyclic pattern. So one example that I thought of was maybe you're looking at crime rates predicting how many police are in an area. So when crime is higher, then more police are hired. But it could also be true that there are more police, and so that's predicting less crime. And so they kind of influence each other in a reciprocal way or in a cyclic way. So that's simultaneity. And then the fourth cause of endogeneity that we discussed in class was omitted variables or omitted variable bias. And that's just where we fail to include a variable in our model that's contained in the error term. And we address that by including additional controls and pulling those out of the error term. Do you have any questions about those before we move on?
Sorry.
Yeah, Haley.
Just read. Never mind, I can watch the board.
Are you sure? Okay.
And if you're asked this question, it is sufficient to just list them. You don't need to
Yeah.
define them.
Yeah, do explain.
Nope.
You
can-
might have we have no idea. You might have a question that asks, explain what simultaneity is. And in that case, you want to know what it is. But if you get a question like this that just asks, what are the 4 causes? You can list them, and that's totally fine.
And I don't think I actually used the technical name for the first one, where a linear model, you use a linear model on accident when the data isn't linear. That's called functional form misspecification. So if you're listing them, you can just say functional form misspecification, measurement error, simultaneity, and omitted variables, for example. Full credit. Awesome. So next we'll go down to number 7. This is a true-false question. And it says classical measurement error in a dependent variable does not impact OLS slope coefficient estimates. And this is true because measurement error in your dependent variable won't actually change the overall relationship between X and Y, although it might change the variance of the residuals or standard errors. If this said independent variable, then you would say, yeah, that actually does impact OLS slope coefficient estimates, because that's when endogeneity would be a problem. You would have your X's correlated with your error term. So the answer to number 7 is true.
Okay. Any questions on that concept? Okay. So next we'll move on to 11. I'll pause on that for just a second while you guys are getting that note. Okay, so if we go down to question 11. Oh, I missed this highlight. It's asking us the error term in a regression equation is said to exhibit serial correlation if blank. So what do you guys remember about serial correlation? It's one of our things that we don't want to have, right? It's one of our violations of our assumptions. What does it mean if we have serial correlation? Yeah.
I'm not sure about this, but it's like when you're looking at panel or longitudinal data, like it's that you're getting the same person or the same couple over and or not the same person over and over again, and you're measuring them, and then they're going to correlate with each other, and we don't.
Yeah, exactly. It's when multiple data points in our data set, the errors correlate with each other. Either because of, like you said, Anna, we have panel data where people are in there multiple times. So they're more similar to themselves than they are to anybody else in the data set. Or if our data is not independent, meaning we could have couples, we could have families, we have people that are more correlated with each other than some other random person in the data set. So knowing that's what serial correlation is, what would you guess as the answer to this question? There's only one right one.
Did you have a hand, Jenna, or?
Oh, sorry, I was going to be.
Oh,
Yeah.
okay.
B.
Oh, that's
B
awesome.
is correct, because that's just another way of saying that our data points are correlated, right? Is that their error terms have non-zero covariances, which if we were to kind of simplify that and decipher what that's saying, it's saying the error terms are covarying. They are correlated. The other answers are just distractors. They have nothing to do with serial correlation. It's really about those error terms being related, which covary is another word for that. Okay. So number 15 asks you guys about a Hausman test. You do not need to know this. So this is on the practice test. It's also on the other practice test that was posted on Learning Suite. You don't need to know how to do a Hausman test.
We just didn't get that far in the
Yes.
content,
So
so don't worry about it.
don't worry about that.
Your class that good, we didn't.
We did.
Good.
Very-
That's
To be fair, I think we like learned it on the very last lecture and I barely understood it, so it's good that we don't have to explain it to you guys because I don't really know it either. Okay, so don't worry about that. All you can know is it's a way to test for endogeneity, but you guys won't have to explain how that works or test for endogeneity on your exam. Okay, so let's move on to 16. Okay. So it says this is a histogram of the residuals resulting from a regression that used a linear probability model. What do you guys remember about a linear probability model? When do we use that?
We have a binary
Yes, exactly.
and we're using the line.
Exactly, yeah. So compared to a logit or a probit that are more, we're using a different distribution for those. This one, we're using the same linear function we would to estimate any regression, but for a binary outcome. So just eyeballing this, what does this tell you about the errors being normally distributed? Basically, that's asking you, are the errors normally distributed in this graph? What do you think based on how it looks?
They're bimodal, so is that?
Yeah, what do you think? What do you guys know about what a normal distribution is supposed to look like?
Well, it's normal for binary, but it looks not normal for linear.
Yeah. So a normal distribution is going to be a bell curve around our mean, right? And so this is not normally distributed because it's bimodal, like you were saying. If this was normally distributed, it would look something like this right over the middle. It's a horrible curve, but you know what I'm trying to say. And so what you would say here is you would want to say, well, looking at this doesn't look like a normal distribution because normal distributions are centered around the mean and are in the shape of a bell curve. They're not skewed to one side. And here we're seeing two clear curves, right? Which is not normal. So this is expected for a linear probability model though. And I'll explain why. And then I have an explanation that I'll show you guys that you can write down. But basically in a linear probability model, what we're doing is we're fitting a linear function to an outcome that's binary, right? And that's like, there's some error in that. Because our dependent variable can only be like a 0 or a 1, there's only two outcomes. Our errors or our residuals, which is what's in this graph, have to kind of make up for this difference between our line and our two outcomes. And so that just makes our errors look a little bit strange, and it creates that strange pattern. And so if I were to explain that on the exam, I would say something like this, right? We would want to say, this is a bimodal distribution. So no, it's not normal, because normal would be centered without skew. And this is expected because our errors are making up for that difference between our linear function and our binary outcome, which just leads to some strange shapes. That's really all you need to say. Yeah.
So if we have this exact same question, just happens to be on the exam, are you gonna be like, oh, you just copied word for word what I wrote? Or do
You should put it in your own words.
Okay.
Put it in your own words.
Yeah.
Just making sure like.
Yeah.
Every word couple is the same. Yeah.
Yeah. Yeah.
Will this look different for logit or?
That's a good question. I don't know if you'll need to know that. I think it would be different, I'm
And they're
assuming.
not, the S curves on those are only slightly different, so it would probably still look really similar.
It might. That's a great
for those
question.
visuals.
That's a great question. I actually don't know.
I
don't know,
think
do you have
that, I think that this would look, I think it would look similar in terms of like the distribution. I just think that the other models would still obviously be better because you are looking at an S curve and you can look at the margins for those binary variables, whereas I think Jocelyn said that's why we rarely use linear probability models, because they just don't,
Yeah.
don't fit the data as well.
Right. I think the point of this question is she kind of wants you to see the difference, or like the way the errors are shaped when we're using this linear function, which is unique to the linear probability model, and how that looks weird because we're using it to predict binary.
Yeah.
So I think
that
it's
makes sense.
unlikely that you'll have to answer it about a logit or a probit, but if you do, I'm sorry that I told you the wrong thing. Okay. You might also get a question like this. I don't know. It was on the other practice exam. How would you address this issue in your research if this was the case? Like if your errors looked like this? Any ideas? You could, yeah. You might not have even used an LPM to begin with because of this. What you can say if it asks you how would you address this, I put down here, think central limit theorem and sample size. Basically, this is not an issue if you have a large sample, right? It says how would you address this issue, but in reality, this is not an issue unless you have an extremely small sample. Because that central limit theorem tells us that the more people we have in our sample, the closer we're going to trend towards normality, no matter what our distribution of the errors look like. Our X's, our estimates are still going to be trending towards normality because we have a large sample size. That's what the central limit theorem says. So unless this was specified of like, oh, there's like 10 people in this sample, then that would be an issue. But more likely than not, you would just say, actually, due to the central limit theorem, we don't need to change anything, but we would address in our research paper that we have this, weird error shape because of LPM. That's expected. And we're applying it to the central limit theory. We don't expect it to be an issue. Okay, moving on to our long answer about heteroskedasticity. Okay, so it says consider a regression model. Don't worry too much about this annotation. Really, it's just saying that there these errors. Basically, it's just saying that we have a regression model where we have homoskedasticity violated. Okay, our the variance of the errors is not constant, is what heteroskedasticity means. So, are the estimated beta coefficients biased or unbiased when heteroskedasticity is present?
Unbiased.
Correct. You're right. Do you know why?
The standard errors not right, so they can easily classify the question.
Yeah, that's beautiful. So the estimator itself is not the issue, right? It's the standard errors, right? So how you would answer this first question is just something like the OLS estimator is still unbiased when heteroskedasticity is present. Our coefficients we're not worried about. They're the same, okay? So you don't have to explain that for that question. You could just say they are unbiased. But moving on to B, like Kyra said, it asks, how does heteroscedasticity affect the estimates for standard errors? Now, this is different. The standard errors are biased, okay? That's because when we have heteroscedasticity, the standard errors are often too small, which is leading us to more type 1 errors. That just means that we are rejecting our null hypothesis more than we should. So I might write something for this one like heteroscedasticity results in standard errors that are biased. We could say something like they're often too small. Leading to type 1 errors. So basically,
False positive, right?
yeah, that's when we're saying, oh, there's a relationship here when there actually isn't. So the issue here is not that our coefficients are wrong, it's that our standard errors are wrong, which affects our hypothesis testing. And it's giving us a lower p-value when maybe that's not actually accurate. Yeah.
When you use the robust command, would the p-value change if it was impacted by this?
Yeah, great question. And we'll get to that because part of this question is going to ask, what do we do about it?
Oh.
And that is what we do about it, right? We use the robust command. And what that does is it gives us some larger standard errors. It accounts for that error or that issue. It gives us some more robust or larger standard errors, making it harder for us to get that type 1 error, making
But
it.
does the p-value change if it needs to?
Yeah.
And I think that some of you saw this with your papers. Just because you did test for heteroscedasticity and find that it was present. And so you used robust standard errors. And lots of you were saying, oh, that'll change a lot about my tables. Like maybe that'll change my coefficients. Your coefficients didn't change, but there is a chance that those p-values changed and that you would be rejecting or failing to reject the null hypothesis differently based on those robust standard errors being included. So that's why this is so important.
Yeah, depending on how big that heteroscedasticity issue is, you could have like a p equals 0.03 and you're like, oh, this relationship is significant. But then you use robust, it could be like 0.051 and you're like, oh, never mind, so that could happen just because this is allowing us to be more sensitive in our hypothesis testing, more accurate. Okay. All right, this is a long one, so bear with me. You're going to want to do a bit of writing on part C. Okay, so it's asking, how is heteroscedasticity detected? Describe the intuition behind this heteroscedasticity test and describe the White test in detail, including how you would conduct it. Okay, so you might get something like this about a White test. You might get something like this about like a skewness kurtosis test. Just be prepared to like understand not only how you do one of the tests to correct for these violations, but also be prepared to explain kind of like, what's the intuition behind it? What does this mean that we're doing this test? What is it actually doing? Okay, so I'm going to talk you through this and then I'm going to show you what an answer could look like. So basically, the way that we detect heteroscedasticity, that first question, is we use a test such as the White test to determine whether there's a relationship between the variance of our errors and our x variables, right? Because all homoscedasticity is saying is that as our x value changes, the variance of our errors should be constant, right? And so heteroscedasticity is the opposite of that our x variables, based on their value, the variance of our errors are changing. There's a relationship between the two. Our x's are predicting the variance of the errors. Okay, and so that's how I might answer that question of how we can detect it and what is the intuition behind this test. It's testing for that systematic relationship between the x's and the error variance. Which in lay terms means, does knowing the x values help us predict how spread out our errors are? Is there a predicting relationship? Okay. And this will be on the recording to get that. Oh, ignore that one. Okay, the next part of this question is to describe the white test in detail, including how you would conduct it. So we already kind of said what the white test does. And so you have a couple ways that you could answer this. Okay, you could walk us through how to do a white test using these steps. Okay, right, we estimate the model, we save the residuals, we square the residuals, then we run a regression of the squared residuals on all the explanatory variables and squared explanatory variables. And then we use an F-test to see if it's significant. That's one way you could explain how to do the white test. A simpler way, which I would probably prefer doing if I were you, is this simpler code that she taught you. Yeah, you can estimate the model, and you might want to give us examples of like, what would you type in? So I have an example there of regression YXX, right? That would be how we would run it. And then you run the white test, ESTAT IM test white. This should be in your notes or in one of Jocelyn's coding files. And then you would use a Chow test, which is also called an F test, to interpret the significance. That's a much easier way to do it. So you can do either is correct. The last thing you would want to explain is how to interpret that significance. So what do you guys remember? When you ran white tests and you ran that F test at the end, what did it mean if your p-value was lower than 0.05? Does anyone remember? Yeah.
And your data was heteroscedastic, or there was heteroscedasticity in your data, which means you need to account for that.
Exactly. Because if you think about it, what this is testing, just like in any other hypothesis test, we're testing for a relationship. And if you remember, the intuition behind the test is there a relationship between our error variance and our x's? So if it's a significant p-value, the answer is yes, there's a significant relationship, which means heteroscedasticity is an issue, right? So I have here, if we reject the null, meaning our p-value is less than 0.05, there is a relationship, meaning we have heteroscedasticity. That's the problem. If we don't reject the null, we have no problem, and we don't need to adjust the model. Okay. So that question is a bit hefty. Okay, just anticipate if you get a question like that, there's a few different questions in there that you want to make sure you're hitting. How is it detected? Explain the intuition, explain how to do the test, and tell us how you would interpret it. Okay. All right, this one's very easy. Kyra already answered it for us. Let's say that heteroscedasticity is found in the data. Explain the adjustment you would make. This is going to feel relieving after such a long answer. Add robust to the end of your code. Okay, and we already explained what that's doing. That's fixing our standard errors.
So do you just write?
It's comma robust, but yeah, technically it's reg, your whole equation, comma robust. Okay. All right, let's move on to our other Unit 3 question. So Hannah, I have these all written down. I just didn't write down the first one because it was long and I didn't.
Yeah, no, that's okay. Awesome. So these are a series of questions about dealing with violations of the OLS assumptions, which you all just went and ran tests to see if these assumptions were violated for your papers. So these should be pretty familiar to you. But the first one is asking how we would test for non-normal errors and how we would address non-normality in errors if it were present. Do any of you want to give a stab at how you would test for non-normal errors? Or like the distribution of errors being non-normal? Yeah, go ahead, Jenna. Yeah, you got it. So for people who are watching the recording, in case you couldn't hear that, you would be doing the SK test to check for skewness and kurtosis, or you would conduct the Shapiro-Wilk test, which tells you if the distribution approximates normality. I think in that output, it also tells you skewness and kurtosis. But this is less of a concern if sample size is large. And several of you who found that your data was skewed or that there was evidence of kurtosis for your papers, you just made a note in your paper saying that you appealed to the central limit theorem since your sample size was large, so it wasn't a concern. If you did have a small sample size, however, you would address non-normality in the errors by transforming the data. So you would probably just try a few different data transformations to see if that helped the data to appear more normally distributed. Yeah, go ahead, Jenna.
Which transforming the data, is that like entail taking logs or? What is
Yeah, like there are a bunch of different ways you could transform the data, but like squared variables or taking the natural log of a variable. I don't know why those are the only two that are coming to me right now.
It's the only two I know.
I feel like there is another one that I had on the tip of my tongue, but I can't think of it right now. So yeah, that's how you would test for and address non-normal errors. And then do any of you want to tell me how you would test for heteroskedasticity? Julia just went over this, so maybe we actually won't go through this
Anyone
in
remember?
great detail. Let's just save our time. So yeah, you would conduct White's test. And then if this test is significant and indicates the presence of heteroskedasticity, then you would address this by using robust standard errors. And let's leave it at that. I thought Julia did a great job explaining that one.
Perfect. I'm just finishing up one more note on this one.
Yeah, that's great. No rush. Okay, I'll move on to letter C then. This one asks how we would test that items in a scale variable measure the same concept and how you would address this if items didn't align well with each other. I'll open that up to you guys too. Yeah.
Chromex alpha, right?
Yeah. Yep. So for this one, all you would need to say is that you would calculate reliability for the scale or determine Cronbach's alpha for the scale, which basically just tells you how correlated or intercorrelated all of the items are with each other. And if your alpha was low, then you would examine factor loadings, or because that's not something we really talked about in this class, maybe you would look at a correlation matrix to see, oh, like which items are correlating poorly with each other. All you really need to put for this, if when it asks how you would address it if items didn't align well with each other, is you could even just say, I would drop the variables that were not highly correlated with each other, and that would be sufficient.
Or you can
So-
also put the individual items into your regression. Like if
Yes,
that doesn't
that's
work,
true.
then you could use each item as its own predictor or its
Instead
own
of-
dependent.
Instead of putting them all together in a scale, just putting the individual items. Awesome. And then for letter D, how would you test that explanatory variables in a model are not too correlated with each other? And how would you address this if there is an extremely high linear correlation between two X variables in a model? Yeah, Kyra.
Just the Hausman test that we did learn.
No, this isn't the Hausman test, but
I guess for
multi-collinearity.
multi-collinearity.
Yeah.
VIF, right?
yeah, this is multicollinearity. So you're going to be looking at it's called the variance inflation factor, or VIF. The code is like super simple. I think after your regression, you just type VIF. And that tells us how much a given variable inflates the variance for the other variables. But essentially just tells you if the variables are too correlated with each other, or if they overlap so much that they're kind of taking over each other in the model. And so how would you address this if there was an extremely high linear correlation? Then the variables with a VIF higher than 10 well, I don't want to say this backwards, just a second.
You're right. That's what
Yeah, so you would drop variables with a VIF that's higher than 10. Just because they're essentially already included or accounted for in the model because they're kind of absorbed by another variable that you are including. Awesome. I don't know if you have questions on any of those under diagnostics and dealing with violations, but that's all of the new material that might be tested for on the exam, or at least the basic concepts. I think we're good to open up for other questions too now. If you have different concepts you want to review from the first 2 units or just any questions in general. Yeah, go ahead, Kyra.
Can we go over an example of hypothesis testing?
I feel like there are so many different ways to do hypothesis testing. Oh, okay, thank you. Like on the practice exam?
Just, yeah, besides that, hypothesis testing is the hardest thing.
Okay,
Especially when they're joint.
yeah, no, that makes sense.
Yeah, we can do that. That one is gonna take a little bit more time. So let's, when do you have to go, Kyra?
2:10.
Okay. Let's see if there's any other like quick questions about concepts or things to go over. We want to answer those first, and then we can walk you through that for anyone who wants to stay.
Yeah,
Is
I
that
was going to
something?
say too, there are so many different types of hypothesis testing. So if number 3 or number 2 is the one that would be most helpful for you, Kyra, then we can go over that one after. But you'll notice that number 3 is also a hypothesis testing question, but it's just like a different type of hypothesis testing. And so that's like, I just feel like hypothesis testing is very general. So I agree with Julia. We can go over it at the end of the review session with you if you have a couple minutes, but if you have something more specific that you would like us to go over,
No, that's
Then-
all good.
okay,
Yeah, we can definitely walk through one though.
yeah,
Um,
we totally can.
also, what will really help with number 2 is for midterm 2, I did a video on a moderation hypothesis test that is similar to this one. I would review that. But yes, we can go over that one.
And then number 3, which is a different type of hypothesis testing. I think that this question resembles one from midterm 1.
It might be.
It might be, I think it's actually exactly the same as the one that you were given on midterm 1. So I would definitely,
Because there's a video I can watch.
well, we're happy to go through it.
Yeah,
too.
well, I think we can
weren't
still go
trying to
through it.
shut you down.
No, no, we're not shutting you down. We just want to make sure
We're
there's
just-
other.
Letting you know
If
where
there's
to
other
go
questions,
if you have questions that come up on the test. And like I said, I would definitely recommend reviewing your midterm 1 and midterm 2 feedback. Yeah, go
I
ahead,
feel like
Kyra.
it's less just about what was on those tests and just like what we did in class and trying to test different things, like the joint. testing,
Yeah.
That kind of stuff, but that's just a general thing that I want to be better at.
You brought up joint hypothesis testing twice, so maybe we could at least go over that after.
Cool.
Yeah, that's great. Yeah, Jenna.
I also have questions about hypothesis testing. My question is if we could review this, I don't know how to describe it, but it's like where she like had those equations where it was like, okay, we're adding on like beta 1, beta 2, beta 3, the moderator, and then we're like slowly crossing stuff out, and then this is like what we're finally plugging into this data. I don't know what to call that concept, but it is part of hypothesis testing. And it seems like it might be part of number 2 on there that
Yeah.
I'm going to figure out. But
Yeah.
that can
Then-
also be an thing. But
Would that be something, because you both have brought up that, would you guys rather just walk through that? Is there
We
any
can
other?
just go through number 2 if that
Yeah,
would be
we
the
could
most
spend the rest of the
helpful.
time doing that. Does that sound good to everybody?
moderating.
Okay, let's do it. I think this is probably the trickier. Moderation is tricky, and this question particularly is good to practice because it's gonna have you calculate some stuff, not just use data. So
You'll
we
have
can go
to
through that.
do some things by hand on this one.
Okay. Does someone want to read our introduction for us in part A? Yeah, go for it.
This question is a data exercise that requires you to use some Morgan's data. Use the data set called and the accompanying data found in Morgan's speed. This data set measures information about parent time with children. Each observation is a parent-child dyad. The variables of interest are total time, minutes per day a child or parent spends with the child. Female, a binary variable indicating if the child's a female, and parent female, a binary indicating if parent's female.
Okay, all right. So if you want to follow along on Stata, we will not be able to project it up here, but you guys can pull it up if you want, and we'll pull it up and do it up here as well. Okay, so our variables of interest, total time, I think that's our outcome. We can see here. That's our outcome. Oop, that's an eraser. Okay, and then we have our intercept, which is beta naught. We have our x1 is female, x2 is, which is the child's gender, x2 is the parent's gender, parent female, and then we have this, oh wait, okay, I thought the question was going to ask which one's an interaction. And then we have this interaction term between child gender and parent gender, right? So this question is basically asking, I think total time is minutes per day a parent spends with a child. So we're trying to see, how does the child's gender, the parent's gender independently relate to that, how much time they're spending together every day? And then also, is there an interaction between those two? Are they jointly correlated with that? Okay. So how would we draw a moderation model or figure to show that? Have you guys ever drawn a moderation model? What does that normally look like? That's too small. 1 second. I'm like, I need to write in this. Okay, so we would have a box with child female, right?
And then there would be an arrow pointing to the box on the right.
Love
There's
it.
gonna be a box of the middle of those.
Sorry, I could above or below. You're good.
Wherever there's one.
Wherever there's-
Female, the middle of that.
Perfect.
And I
Love it.
did
Good
want to
job.
point out here too that it says that we're studying differences by gender, but you'll notice that that interaction term is between child gender and parent gender. And so this is an example of where you might just write on your exam, like, I'm assuming that it's parent gender that's moderating this relationship, or I'm assuming that it's child gender that's moderating this relationship, just because it doesn't specify whose gender you're actually moderating by. So,
Yeah, this is interchangeable.
so
If
those
you-
are interchangeable, yes. is what I'm
either
trying to
one
say.
could be the moderator. So yeah, just specify, like Hannah said, when you draw that, we'll see which one you're treating as your moderator. All right, then we're going to estimate the regression model, which we can't do on the iPad, but that's what you would do in Stata, right? Your code might look something like reg total time. And then whenever we do an interaction, you need to have the main variable, each of the main variables in on its own, right? So we might have female. What's the other one called? Parent female.
Mhm.
Then you would have the interaction term. I think Jocelyn teaches in this class to create your interaction term first. So whatever that is, we'll just say female, female. I'll erase that so that's not confusing. But let's say that that's what we called it. Okay. So we have everything in there that we need. You don't need to write anything here. You would just do this in your code. But you do need to interpret your results. So this is just like she's taught you throughout the class, right? You would say, you would explain each of your coefficients. You would say what it means, whether they're significant or not. So if we want to walk through it, I think Hannah's working on getting it up. We might be able to, we might not be able to.
It's wanting me to log into Box again, so I can't open the files right now, but
Do you want to try to get it up on mine?
I know that who had it open with me during office hours today. Yeah, I don't know if it like would refresh
actually-
quickly.
Hold on, I think I can get, okay, I have mine up. Sorry, I should have just done
It's
it
just
on mine
taking
because I
so
have it on my.
long.
Okay, I have it up. I won't be able to
I'm
show you,
happy
but
to like,
do you want to do
be
it?
on the
Sure.
computer and working on it while you're talking.
And when you say interpret your results, including information, they want you to type it into Stata code, just like with the green.
I don't know why. I guess it says do this in your Stata code. You could type it in your little do file, or if there's room on the exam, you could like write it there.
Or just do it on the back and say.
Yeah, do it wherever you want to do it. I don't know why it says no need to write anything when it says interpret your results. Did you do it? Maybe not. It says
What does it say?
interpret, but then no need to write anything. Maybe it just
I
wants you
think
in your
it's more
mind to
just-
do it. You think that's what it is?
Yeah, I honestly feel like sometimes there are little questions like this or instructions, but then it's saying this is what you're going to be doing during the following,
Hmm.
because you're going to be interpreting
Yeah.
your results, including information on all of
That's
those
true.
things in the following like questions. So if it just says don't write anything, just don't write anything and assume you'll get it.
Yeah, okay,
Yeah,
just don't
it's
write
good.
anything there.
Yeah.
Just look at it and interpret it in your head so that you're ready to answer the other questions. Okay. Okay, so we'll grade you on whether you
Hopefully
do
that's
that.
right, yeah.
We will look at your code though and make sure that you did it right. So that's where you'll get points for B.
Yeah.
If you get this question. Okay, C, using a t-test, perform a hypothesis test that B. Let's write out our equation. Oh, we have our equation. Okay, so beta 2 would be this one. What does it mean if we're doing a hypothesis test that beta 2 equals 0? What are we comparing beta 2 to? Well,
Father's something.
my question was unclear actually, but yeah, so we're looking at whether there is a significant relationship between being a father or mother and total time, right? And so what would we look at on our output to see if beta 2 is significantly different from 0? Yep. That's right. So for this one, you would just look at the p-value. Make sure you're not getting your beta 2 mixed up with another one. This is one where Jocelyn could give you this question and she could say beta 1. So just make sure that you're looking and seeing that there might be differences between this version and that version. So for this one, I think parent female, right? And then you just report that to us and tell us, how do you know if it's significant or not? What does that mean? Okay, this is where it gets a little tricky.
Yeah, this is where you need me to catch up to you.
Actually, I just need, can I see the answer key? I just want to write out the.
Yeah,
Are
go
they
for it.
coming? Do you want to?
Yeah,
check
I can
if-
go talk to them.
I thought it might be over because class is over.
I would also be happy to make a little video walking through this if needed. So that'd be really nice.
If we don't finish.
No, I need to know if you're ready.
Okay, we're good, guys.
He's peeking out the first, so.
Okay. He's just snooping.
I think he's looking for something.
Okay, let's write out our equation with the numbers from our output. Okay, so this is what I would suggest that you do with all of these subsequent questions is write out your whole equation or else it's going to get confusing, okay? So our entire equation, let's start with our y, you could write total time, whatever, equals, and then we're going to look at our output. If you're following along, oh, it's a little different than,
Yeah, that's not right.
oh, you're missing the interaction.
Oh, yeah.
You don't have to create a new one. You could just do female star parent underscore female.
Okay, I already created it, so maybe I'll
okay,
just go to the do file. I don't know where the do file is. This is a little different than.
Sorry. Yeah, it's.
No, you're good. I just forgot to include it.
Oh, you got it.
Moderator. Okay. Is that right? Yeah, those numbers look correct to me.
Yep. Yeah.
Mhm.
Okay, so we just ran that code that we had written down, and now we're looking at the numbers to write down our equation. Okay, so we have y equals beta naught. So what is our beta naught? What does that translate to in our output? A constant. So we'd write down whatever our constant is. And this is recording, so if you guys need to go, you should be able to go back and see this.
Yeah, bye, Carly.
Good luck. Okay, and then we're gonna plug in our other numbers. So we'll have plus beta beta 1, which is our child gender, which here in our output is actually negative. It's minus 9.54. Okay, then we would put in our parent female coefficient, which on here is 113.02. Do not rely on these numbers for anything. Okay, make sure you're doing this on your own because it could be a completely different data set that it's asking you to use. And then we want our beta 3, which is our moderator, which on here is 19.01. So what is the average time fathers spend with their sons? So if we were to plug that in mathematically, yeah, Anna, either. Sure. I'm just including it because it's part of our equation up here that is given to us. So she specifies the model for you here, and we see beta 3 is our moderator.
Oh, sorry, I thought we were on like actually.
And we're just filling it out so you can see what those different
Yeah.
numbers are.
Yeah. Okay, so let's think about this for a second. In this situation, we want to know the average time fathers spend with their sons. That means that female and parent female is, I mean, both are boys, right? So if both are boys, what would the value of female be? Yep. So the value of female would be 0, and the value of parent female would be 0, right? Because we're assuming this is a binary variable where female equals 1 if you're a girl,
0
right?
times 0 is 0.
Exactly. So, and then this would be 0 because, yeah, exactly. So which number would we use in this equation to tell us the average time fathers spend with their sons? If we were to just, right, it would just be our constant, right? Because our constant is when all of our x's are 0, if they're all 0, right? And we could walk through that if we wanted to, just plug 0 into everything, and that would all cancel out, and we would be left with our constant. And then I'm assuming, is it seconds, minutes? Probably not seconds.
I think it's minutes. I hope it's not seconds.
I'm like, I expect to only spend 300 seconds with my child. Okay. Now let's try it for mothers and daughters. So we would do the same kind of thing with our equation, but we would be plugging in a different value. What would we be plugging in for each of our? Right. Yeah, because x would equal 1, right? Here, x1 would equal 1, x2 would equal 1. And then here, if we want to think about this in another way, our moderator is the same thing as saying x times x, x1 times x2. Okay, so we would plug it in here as well. This would be 1 and this would be 1. So then we would want to condense that equation, and basically 1 times 1 is 1, anything times 1 is itself, right? So we would end up with 323.93 minus 9.54 plus 113.02 plus 1901. Do you understand how we got there? Okay. And so the answer to that, I'm not going to do that, but the answer to this would be our answer in minutes.
446.43 minutes.
446.43. Does that kind of make sense intuitively how we got there? All we're doing is we're plugging in values in our equation. Okay, now it's asking, is father-daughter time equal to father-son time? This is a hypothesis test question. The trick is, which beta are we doing a hypothesis test on? And it's not as simple as that, because
I'm not sure what they have on the answer key, but this one,
let's see, it should be the same.
this one you actually just look at the output for F, but then I think on G you do a test. So are you on F?
Yeah, F.
So essentially here,
Oh.
because you know what father, daughter, or I guess is father-daughter time equal to father-son time?
Oh, okay.
So the beta not coefficient or constant represents father-son time. And then maybe if you want to walk through what would represent father-daughter time.
Yeah, so
you-
you see how on this one, the parent gender is the same. We're looking at fathers in both of them, right? So we're not going to be looking at the interaction term here because
Mhm.
we're just looking at, does daughter and son time equal for fathers? And so if we were to plug that into our equation, let's just do that again. I think that's the easiest way. Like when you are confused, go back to the equation and plug in the right values for your x's, okay? So going back to this equation here, we want to see which betas are we actually testing here. And so if it's a father, which of these x's are equal 0? This one does, right? So this this is not applying to us right now, right? We're taking that out of our
Mhm.
equation. But this is the one that we're looking at, right? We want to look at whether the gender is male or female in the child, because no matter what, our father is 0 right now, so we're not going to worry about beta 2. Does that make sense? And so really what this is asking is, so if we plug in, let's say for father-daughter time, what would be the value of this variable? It would be 1, right? And so we would be basically the father-daughter time is beta 1, right?
The father-daughter time.
Mm-hmm.
Yeah. And then the father-son time would be the constant.
And so we already know that the father-son time is our beta naught because we answered it up here in D, right? So, and then this one also wouldn't apply because it's a father, so we're not using our beta 3 because that's a 0 value. And so that would cancel out. So what I'm trying to show you here is that basically to see if this is equal, we want to compare beta 1 to beta naught. Because if we have a daughter and a father, we already know because father is 0, we are taking beta 2 and beta 3 out. Beta 1 is the only thing that differentiates us from our constant, which is our father-son time, from our father-daughter time. Does that make sense? It's a little bit hard to explain. Yeah, Jenna?
So going back to like the actual calculation of it, where you're computing, in my brain, I feel like I'm comparing beta naught to beta naught plus beta 1 because it's like you're adding it
That's
to the
exactly
constant.
right.
Oh,
Yes.
Okay.
Uh-huh.
So it is
So, like-
setting like beta 1.
Yeah,
Maybe-
sorry, I said it
Okay.
wrong. Mhm.
Maybe I'll stand up here really
Because I was like, where did beta naught go?
So this.
Yeah.
Okay.
So this represents father-son time.
Yeah.
And this number minus this number. Oh.
Oh, I'm sorry. I forgot that that's what you guys are saying.
This number minus that number
Okay.
is father-daughter time. So it's like
Okay.
the question is asking, is 323.93 minutes the same as 323.93 minutes minus 9.54? And so to actually answer the question, you would go to your regression output, and next to beta 1, you would see if that p-value was significant, and if it was, then you would conclude that fathers spend a statistically different amount of time with their not fathers with fathers,
It's so
with their
confusing.
sons versus their daughters. It's hard to talk through these
Yeah.
things sometimes, but yeah. So essentially, this is asking you, is beta naught equal to beta naught plus 1? And this is beta naught, and this is beta 1. And so,
And asking if beta naught plus beta 1 equals beta naught is the same thing as saying beta 1 equals 0.
So if you were to
Yes.
actually run the test, you would plug in like test and then whatever it's called, I think just female equals 0.
Yeah,
And that would be
Yeah,
that.
which
and
is
that
the
would
But you
same
already
thing.
tested that.
Same
which
thing
would
as
be
looking
the
at your
p-value,
Yeah,
but you would
but you
get the
already
same
have that.
p-value in your output next to beta 1.
Yeah.
Sorry, I wish we had our
Yeah,
output up.
Does
would
that make
probably be helpful.
sense? it's confusing to explain. in
Especially when
words.
we're just talking through it without doing it on Stata. I know it's like, yeah, spinning in circles. Go ahead, Bree.
Would you be able to tell who fathers spend more time with, or would you just be able to say it's different? Like if one coefficient's bigger.
Yeah, you
would
could
be
say
able to
which one
say
they
that
spend more time with.
like,
You-
or something.
Yeah, like, I think.
Since
because-
female is negative here, oh, whoa. Then we know that they're spending more time with sons if it's significant, right? Because we're
Yeah.
taking this out of the constant.
Yeah, that's a good question. So fathers are spending significantly more time with their sons than with their daughters. And that's what we see here.
Okay, and then the last one is similar, but this is comparing mothers and mothers and fathers. It's like the
I know,
words.
I'm like mixing
I get.
up all the
Okay.
father, daughter, son, mother.
So again, I think the easiest way to conceptualize this is to plug your values into your equation to know which betas we're working with, right? And then to understand, okay, which beta is the one that I actually need to test. And so in this one, we have our constant no matter what, and their daughters, which means our female variable equals 1, right? So beta 1 does apply to this equation, right? We'd have, if we were to write it out, our equation would look somewhat like this. Now, what about beta 2? Does it matter here? It does, right? Because for the mothers it would, right? So I crossed out what that value is. Here it is. And let me make sure did I do this right? Is that the thing that you had? Because that looks different. Right here.
So this is like the null hypothesis.
Well, I guess this is the
that
answer.
thing- Yeah, I'm like,
Sorry.
that should be right.
Okay.
This is just the null hypothesis that's being tested.
Yeah,
but
that's
this
what I
isn't
wanna
the
get to.
actual Equation.
That's what I
So
want
we're
to get
looking at, I can like quickly fact check it or think through it. I might not do it out loud in case I did it wrong though.
Okay,
So
yeah.
father-daughter
And I'll
time.
think about it too.
Yeah, because father-daughter time would be represented by beta naught plus beta 1. And then mother-daughter time, you always have to include the constant because that's what you're checking against. And then, yeah, mother-daughter time would be represented by all the other beta variables.
You include the interaction variable too?
Yeah.
Here you would, right? Because
Because it's mothers and daughters.
Okay, so what I'm doing here is the reason I write out the equation is it just helps me understand for each of these conditions, which betas are we working with, right? So let's say for the father-daughter condition, father-daughter time is basically, we have beta naught because we have that no matter what, it's our constant. We also have beta 1 because the child is a female, right? So that would be a 1. We don't have beta 2 because it would be a 0 here because it's a male parent. So that would cancel out. And then we don't have our interaction term because, again, because father's 0, 0 times 1, even though we have our female child, that would cancel out because that would be 0, right?
That's
Okay. Then we want to know what's our condition or what's our betas included in the condition of mother-daughter. We always have beta naught. We also have beta 1 because it's x1 equals 1. We also have beta 2 because x2 equals 1. And we also have the interaction term because we're doing 1 times 1 over here, right? It's a female times a female. So we would include this. So basically our hypothesis test is, does beta naught plus beta 1 equal beta naught plus beta 1 plus beta 2 plus beta 3?
So when we plug it in the test, is it just beta 2 plus beta 3 equals 0? Or do we move on to?
I think so. That's how you would condense
Yeah,
it,
you can
right?
even add it like
You could
that there.
condense it like
Okay.
that in Stata, at least based on my understanding.